Greeting everyone, my name is Ali, recently graduated with Master in Electrical and Electronic Engineering from the University of Nottingham Malaysia. Today I will be presenting my final year project that was submitted as my final thesis for undergraduate studies. As the title states, the project elaborates on model development and techno-economic evaluation of a combined heat and power system. In general, the project looks into energy integration and renewable generation. In this presentation, I will look into the future of energy sector and the problems we are facing today and we will potentially experience in the future. I will discuss the background and the applications of combined heat and power systems. I will look into project outline and objectives. I will illustrate the recent developments in this field and justify the novelty of this project. I will discuss the methodology that was employed for this project thoroughly. I will evaluate and compare the simulation results, and I will conclude the presentation by looking into the future perspective of this field. There are various influencing factors such as economic growth, population increase, income growth, and weather conditions that result in higher primary energy consumption as the years go by. The energy demand projection for the case of 2040 is almost 50% higher than today's demand. With all negative disastrous impacts that fossil fuels offer and all the controversial views that the governments around the world faced in the recent years, today, sustainable development is the center of attention and there are considerable funding opportunities and investment on renewable energies. Considering the Southeast Asia, electricity consumption will face 40% increase in 2040, from which renewables are responsible for 30% of that production. So this in fact influenced the financial investment on renewable technologies and their development, particularly in the field of bioenergy, as Southeast Asia is one of the biggest producers of biomass resources. With all that being said, greenhouse gas emissions are bound to increase even higher. The fact that we should remember is that renewable development is not the answer to all problems. This was understood in the last decade as solar emissions increased despite a significant growth in renewable development. We require to revolutionize the structure and go beyond the supply side. For the energy sector to see a considerable decrease in energy consumption and GHG emissions, we require to target the consumer as well as producer in order to change behaviors and engage them in this matter. If I want to explain almost all conventional power systems briefly, I have to say such systems utilize fossil fuels such as petroleum products or coal for power generation. This led to a significant rise of carbon dioxide level in the air, significant climate changes such as global warming in recent years and unknown climate changes in the future, maybe 10 to hundreds of years, and health-related issues. The most efficient of power systems that are available in the world right now can only generate power with an efficiency of 63.0.8%, which is a power plant located in Japan. Energy generation is not just about electricity production. We require other forms of energy in our daily life, in our industries, such as cooling, heating, and transportation. Currently, in most places around the world, the infrastructures are in a way that heating and cooling are being generated using electricity. For example, we have air conditioning units and electrical boilers that are working with electricity to produce cooling and heating. However, there's a possibility to produce such energy forms while generating electricity. In this way, we do not require to consume more electricity to produce other energy forms. If the infrastructure is provided, we no longer require AC units or boilers in our homes. Cogeneration or combined heat and power systems have received a great deal of attention due to their capability of sequential power and heat generation within a single process. In the cogeneration process, waste thermal energy can be recovered in order to produce another form of energy or product. Considering a situation where an igniter-based engine drives a generator that produces electricity, with implementation of a heat exchanger, the waste heat exiting out of the engine in form of hot exhaust can be captured and the heat can be recovered to produce steam, hot water, or processed heat for other applications. This process differentiates this type of facility from other centralized power plants, and it allows more efficient utilization of fuel to a point where the overall efficiency can reach up to 90%. In this figure, on the left hand side and the right hand side, you see two different systems, two different CHP systems. They both work on the same principle of operation. However, on the left hand side you see a larger scale system, while on the right hand side you see a more compact and smaller scale system. The right hand side system generally works based on internal combustion engine. You might have seen CHP generators or Caterpillar generators for smaller applications, while on the right hand side is more larger scale applications that are implemented in centralized power plants, where there's a gas turbines and fuel and air combusted in a combustor. Uh, Here I provide a summary of keywords that will be encountered in the following slides. Integrated energy system. Imagine a system that is capable of producing every energy form that you require, from electricity and heating to methane and biofuel in industry. Community microgrid is a network of interconnected energy consumers where some consumers are capable of producing their own energy and sharing it with other members. Renewable availability is a method of assessment that determines available renewable resources in certain location and evaluates their intensity for energy generation. And finally, the techno-economic evaluation is also a method of assessment in which technical analysis is tied to economic aspects of a system, aiming at detailed evaluation of the cost of energy. For many industries, organizations, or even real estate developers, CHP systems can offer the most significant opportunities to diminish imported electricity from the grid and decrease fossil fuel consumption. Integrating power and heating sector is a promising approach to achieve energy efficiency, fuel diversification, and less environmental impacts. Realizing the true capability of this approach will ensure the accomplishment of energy transition and climate strategies. There is no doubt that CHPs are associated with higher capital costs and investment. However, these facilities take advantage of better environmental performance, reliable energy supply, and if properly implemented, reduction of electricity price. The project outline in this slide indicates the overall purpose of this study, which was development of a CHP system. But there were necessary steps that was taken to achieve that goal. In the first step, a location selection analysis was conducted. In this analysis, factors such as environmental impacts and economic benefits were taken into account. In the second step, renewable availability assessment was conducted. In this stage, factors such as availability of resources and their intensity measurement were of interest to us. And in the last stage of development, required information concerning load profiles, both in terms of electrical and thermal loads, were gathered to determine the demand and its behavior in hourly, daily, and seasonal manner. The overall project objectives states that the project elaborates on renewable energy sources and combined heat and power systems. We review the preliminary research works and realize the state-of-the-art designs. We develop different renewable-based CHP configurations in accordance with the available renewable sources. We implement the suggested models in a case study and conduct a comparative analysis between the different scenarios. And we determine the best dispatch strategy for improving energy storage life expectancy. In terms of preliminary designs, the suggested system on the left integrated fuel cell, wind turbine, and PV panel technology into a single CHP system. Although in such case production of thermal energy is carried out by means of recovering waste heat from fuel cell system, this type of integration might include a more modern technology such as fuel cell, but it is suitable for supplying the required energy for a single household. In our project, we developed an energy system for community in which the demand includes residential, commercial, and industrial sector. So the scale that we considered in comparison with this project is absolutely different. On the right hand side, in the system on the right side, the author suggested one scenario for off-grid electrification. In their study, wind and solar energies were the two renewable resources to generate clean energy. On the other hand, in the current work, the renewable sources are being realized based on availability analysis, and their benefits for power generation. Further, multiple scenarios are being suggested to choose the most suitable system in terms of economic and environmental perspectives. The following slides indicate the steps that were taken to develop this project and in fact elaborate on methodology of this work. The first step is location selection. Selecting a location for renewable development and carrying out studies such as this to investigate the impacts of renewable generation requires to consider several factors. These factors include both economic and environmental aspects. In terms of economic point of view, the location should be associated with considerable GHG emissions that the renewable system can actually make a difference. Otherwise, there would be no encouragement to develop a costly energy system for no significant impacts. In terms of economic point of view, the cost of generating energy and payback period should be low in order to encourage investors for further development. This factor mostly considers the availability of renewables in a certain location. For example, sunlight is available all around the world, but implementing PV systems in Sahara Desert is financially more advantageous than the North Pole because it can generate higher power with higher efficiency and therefore supply more consumers and provide higher economic benefits. These two primary factors should be taken into account in order to justify the viability and realistic implementation of energy system before designing and developing. In this project, Santa Catalina Island in California could satisfy the economic and environmental factors. The second step is renewable availability. The first step to realize the available renewable resources on this island was to look into the climate characteristic of that location. This yielded the sunlight availability of 12 hours a day on average and a wind speed of greater than 2 meters per second on average at the sea level. Moreover, possibility of transporting goods between the main port and California shores and the island suggested a third renewable source, which was biomass. Given that California is one of the biggest producers of biomass feedstock in the United States, this source of energy was a viable choice. In a more precise analysis to realize the intensity of renewable sources determined in the first assessment, GHI, global horizontal irradiance, for solar energy and average wind speed at 50 meters above the sea level for wind speed were measured. The average wind speed that we saw in the last slide was for climate purposes. For turbine installation, wind speed is measured at a certain level, which depends on the height of the wind turbine hub. In this study, the value was at 50 meters. In terms of GHI concentration, this indicator measures the total solar irradiance from the sun on a horizontal surface. This value is of particular for PV installation and it is usually measured with pyranometer technology. For wind speed measurement, we use LIDAR technology. As you can see, the GHI concentration is about 5.2 kilowatt hour per square meter of PV panels in a day, and the average wind speed is 5.35 meters per second. The current power station in the island is Pebbly Beach Generating Station that is owned by California Edison Company. All the available information that are provided here are based on actual meeting records and the work papers provided by this company. The current station owns 6 diesel generators and 23 recently installed microturbines. Out of 6 generators, Unit 2 and Unit 6 are actually supplemental reserve in case of increase in future consumption. The company also owns an energy storage system comprising of 6 sodium sulfur or NAS batteries with 85% round-trip efficiency that forms a total energy capacity of 7.2 megawatt hour with maximum rated output of 1 megawatt. Concerning the Pebbly Beach station generating station, satisfy these electrical loads that are presented in this slide. Concerning the daily profile, The electricity consumption follows the characteristic of a community load profile in a similar climate region. As you can see in the figure, electricity consumption throughout the year is relatively constant as the weather condition and temperature does not vary significantly. The daily profile shows two local peaks, one being at 6 a.m. start of the day and one being at 6 p.m. when people are returned to homes. In terms of thermal load profile, there are no available information on actual heating demand of the island, although the profiles that are provided here are based on similar climate characteristics to the Santa Catalina island and are projected based on average housing area and available residential houses in this island. To estimate the heating demand based on logical data, first a heating profile of a single household located in California with similar climate characteristic was obtained in Homer. Then the heating demand was projected based on the average household area in Santa Catalina and then calculated for the total housing area in that island. The thermal demand also has two local peaks that shows hot water consumption throughout the day. While configuring CHP systems, as we mentioned, we suggested different scenarios to implement and to select the most appropriate one in terms of economic and environmental performance. Configuring different scenarios are carried out based on utilization of renewable sources. 5 scenarios are presented. The base scenario, which depicts the current energy system available in the island. Scenario 1, diesel and solar. Scenario 2 is the integration of diesel and wind. Scenario 3 is the integration of diesel, solar and wind. And then the scenario 4, diesel generators are being replaced with biogas fuel generators and the solar and wind are being integrated as well. The base scenario is based on an existing power station in the island. It was tried to choose the closest rated power to the current operating units in case of generating units. The 23 units of microturbines were combined to form a single microturbine with a rated capacity of 1,495 kilowatts. As you can see in the microturbines is the unit with least GHG emissions. For the energy storage unit, Homer provides sodium sulfur batteries with relatively the same rated capacity and power output as the units implemented in the island. Six battery tanks provide a total capacity of 7.2 million watt hour with a maximum rated output of 1.2 megawatts. The connection of 3 batteries in series was to satisfy the minimum voltage requirement for power converter units. Given that most power converters in power stations operate with a voltage greater than 480 volts, 3 batteries were connected in series to result in 576 volts. For the choice of power converters, we selected MPS 250, 3 units in parallel. In terms of waste heat recovery system that are implemented in scenario 1 to scenario 4, a waste heat recovery was configured in all suggested scenarios. For providing the possibility of heat recovery, 2 options were presented in this study. Either replacing all generating units with a built-in CHP generator, or the compact, such as a small scale compact version that we reviewed in the background slide, or installing external heat recovery systems such as plate heat exchangers and a structure to follow the exhaust gas of generators to the recovery facility and then for further cleaning processes. The first option was not an economic viable approach, therefore the second method was considered in this project. However, in terms of implementation, Homer does not provide the possibility of implementing waste heat recovery system. Therefore, the first option was integrated in the system. However, the installation and the cost of heat recovery system was added to the scenarios as a fixed capital cost. For selection of PV panels in scenario 1, PV panels efficiency was given priority in the system. Therefore, the most efficient panels with 19.7% efficiency were selected for implementation. However, we reduced the efficiency to 17.2% in order to account for power electronic converter and transmission losses. Each panel was capable of generating 370 watts with a maximum power point voltage and current of 40.1 volts and 9.23 ampere respectively. Moreover, installation of pyranometers were considered as well. For such a large solar field, 4 units were added to the system as a fixed capital cost. In scenario 2, wind turbines were selected instead of PV modules. Each turbine had a hub height of 65 meters with a minimum rotational speed of 3 meters per second. The turbines were using permanent magnet synchronous generator as an alternative for electricity generation, with each turbine being capable of generating 800 kilowatts of power. The turbines were connected directly to the AC network using a 4-quadrant 3-phase power converter based on IGBT technology. The power generation at the average wind speed of Santa Catalina Island, 5.35 meters per second, was 157 kilowatt. The wind speed could be measured using LIDAR technology. Installation of 1 unit at $300,000 was considered in this scenario. In scenario 3, we combined wind turbines and PV panels and no technical specifications were changed. However, in scenario 4, all the diesel generators were replaced with Caterpillar products based on biogas fuel generators. Microturbines were kept operational while the other 6 units replaced with biogas generators. These generators were working based on biomass gasification principle provided in this figure. In terms of biomass feedstock selection, sawdust was selected as the best feedstock for power generator since it had the highest heating value. This table shows the financial expenditure associated with every generating unit. Since diesel generators, microturbines, and battery storage tanks are already available in the island, no investment cost was considered for these units. The table presents life expectancy, investment costs, replacement costs, operation and maintenance schedule. The following slides illustrates the simulation results of every scenario. In the base scenario, as you can see, the monthly electric production indicates that the energy demand is satisfied using only diesel generators, while the scenario associated with significant carbon dioxide emission as well as nitrogen oxide emission. The energy cost is relatively high at $0.26 per kilowatt of power. The state of the charge of batteries indicates relatively 40% energy content at each certain period of time. In terms of scenario 1 simulation results, once we added the PV modules to the system, the PV power output indicates an operational of 10 to 11 hours per day on average, and the state of the charge of batteries indicates charging of batteries when solar energies are available. As you can see, in terms of monthly electric production, around 30 to 35% of energy monthly consumption is provided by PV panels, and in terms of thermal consumption, in terms of thermal production, the diesel generators were capable of producing thermal energy. The levelized cost of energy decreased compared to the base scenario to $0.22, while the GHG emission also experienced a significant decrease in the value, as well as nitrogen oxide. By replacing PV panels with wind turbines, the energy cost decreased more due to the fact that wind energy was available 24 hours a day, while solar energy was available only 10 to 11 hours per day. The carbon dioxide decreased as a direct consequence of decreasing the operating time of diesel generators. And the state of the charge of batteries illustrate a rapid energy transition between the AC and DC buses. And as you can see, the turbines were capable of generating more power in comparison with the PV panels in the last scenario. Combining the two scenarios together, you can see a significant increase in monthly electric production by renewable resources, and the diesel generators were still capable of generating thermal energy, and the levelized cost of electricity decreased more to almost $0.2. Carbon dioxide and nitrogen oxide were experienced the same significant reduction in value. In terms of a state of the charge of batteries, here we provided two state of the charge actually. The first one is based on predictive dispatch strategy, and the second one is based on cycle charging strategy. As you can see in predictive dispatch strategy, the rapid discharging and charging of batteries were eliminated in order to increase the life expectancy of battery units. So as you can see, in most of the times, the dispatch strategy actually waits until the battery reaches to 20% of energy content and then attempts to charge the batteries. While in cycle charging strategy, as you can see, the batteries are rapidly charged while containing more than 40% of energy content. So this actually decreased energy throughput of the battery, but increased the life expectancy of batteries by almost 4 years. And in the last scenario, when we replaced diesel generators with biogas fuel generators, we actually formed a 100% renewable based energy system where the energy cost was at $0.21 per kilowatt. The operating cost remained constant, while the total net present cost was increased significantly. The carbon dioxide decreased significantly, and the nitrogen oxide was almost negligible to account for. The average feedstock per day that was assumed per day was almost 39 tons per day. In terms of comparative analysis, the first table presents environmental performance of each scenario in terms of fuel consumption and CO2 and nitrogen oxide emissions. As can be seen, installation of PV panels cut the fuel consumption by 33% and lessened carbon dioxide and nitrogen oxide by 26 and 32% respectively. Comparing with scenario 1, additional saving could be obtained by implementing wind turbines rather than PV panels, in which fuel consumption, soda emissions, and NOx release dropped by 19%, 9%, and 20% in the respective order. Integrating the two renewable technologies in scenario 3 propose a system in which fuel consumption decreased by additional of 28%, carbon dioxide emissions by 27%, and nitrogen release by 27% comparing with scenario 2. The best system in terms of environmental performance was the last scenario, where diesel fuel was replaced with sustainable biomass resources. The next table presents financial expenditures as well as energy costs in all scenarios. The first 3 scenarios resulted in significant economic advantages and lower energy costs in comparison with the base scenario. It could be observed that the installation of PV panels alone resulted in 28% reduction of fuel expenditures. Although the system added a capital cost of almost $4.5 million, but it was capable of decreasing the net present cost by 13%, which consequently gave rise to lower levelized cost of energy by 14% in comparison with base scenario. The majority of cost saving that came with this implementation was due to lower fuel expenditures as well as CO2 tax. Installation of wind turbines reduced fuel expenses and levelized cost of energy by an additional of 14% and 5% respectively. Wind turbines were capable of satisfying more electrical loads due to their availability 24 hours a day comparing with PV panels. It should be noticed that such implementation requires 35% higher financial investment since each turbine can cost up to $2 million excluding installation and maintenance costs. In scenario 3, where wind turbines and solar system were combined together, the financial advantages were presented primarily in form of fuel saving, in which the fuel expenditures were dropped by 27% and 37% in comparison with scenario 1 and scenario 2. The levelized cost of energy in this scenario witnessed additional of 6% reduction in value comparing with scenario 2, and it presented the lowest LCOE cost amongst the other scenarios. Replacing diesel fuel generators with biogas-based units doubled the capital cost comparing with scenario 3. Additionally, more expenses were followed by fuel expenses in which the value was also doubled in comparison with scenario 3. Higher fuel expenditures and required capital costs gave rise to higher levelized cost of energy by almost 50% in comparison with scenario 3. Although the system could save on operating and maintenance costs and so the tax by 5% and almost 50% respectively, but the additional expenses raised the net present cost by 50%. In this scenario, cost of biomass resources was considered with transportation cost to the island. In terms of importance of this study and the emphasis that should be given to this subject is that integrated energy system is looking at how energy systems can connect together. There is usually a commitment to looking at the big picture of our energy systems in the future. With current developments in renewable supplies of electricity, emerging consumer devices, IoT, Internet of Things, energy storage, and smart buildings, energy systems integration is the process that brings them all together into a system that provides value for consumers as well as keeping the lights on and keeping the cost of energy affordable. It is time to make a change in order to step closer towards energy transition and achieving a zero carbon society in order to save our planet for generations to come. If we get this right and if we continue to progress, we will find a way to avoid having to choose between reliable power, clean power, or clean power and affordable power, or grid connected and off-grid energy systems. We truly solve one of the biggest associated challenges that we face in a way that we will endure for generations to come. But in terms of future perspective of this field, well, predicting future might not be the brightest idea, but with a clear understanding of negative impacts of conventional energy generation on the planet and the living species on it, there is no doubt that CHP will be featured in all future energy scenarios. Depletion of fossil fuels and the growing concerns over the primary energy consumption would ensure the long-run existence of this type of energy generation, where heat as well as power is demanded. The developments in the field of multi-energy generation is carried out with respect to many aspects. While optimizing the performance and existing systems is of interest to many industries and energy sectors, possible integration of hybrid system is also important to energy transition goal. In future scenarios, it will be likely to see the large integration of CHP units for satisfying thermal demand. In such scenarios, the interconnection of multiple CHP units would allow satisfaction of thermal energy, while the excess electricity is either utilized in future processes or exported to the grid, providing higher revenue for the system. Similarly, utilization of renewable energy sources such as biomass in CHP systems or developing hybrid CHP configurations will be the mainstream topic that will provide the largest future opportunities. Looking into the future, the international strategies imposing low carbon emission may force the attentions towards technologies cooperating with this condition. Bioenergy for sure will be the first option to look into, as this is the most versatile energy source available. Biomass will remain the most important sustainable energy that can be utilized for production of heat, power, transportation fuels, as well as biomaterials. The future prospects of bioenergy will depend on its competitiveness as well as sustainability. In the following years, the energy future of the world will witness considerable developments in this field. Thank you for your time and your attention.